In this video, we're going to continue our discussion of biasing references and regulators, but we're going to focus on references. Remember that we distinguish between a reference circuit and a bias circuit in that a reference circuit specifically provides absolute constants. That is, a reference circuit can be relied upon to provide a very specific number of volts or amps of current within a pretty tight tolerance, whereas a bias circuit is relied upon more to provide a certain amount of current that will keep certain transistors biased in active mode or in triode or to meet a certain performance requirement and so on. So because a reference circuit provides an absolute value constant, it's usually associated with interface circuits that have to deal with the outside world. So if you imagine, for example, an overall analog integrated circuit, the user of that integrated circuit doesn't particularly care what the voltage swings are internal to this integrated circuit. There might be swings of 200 millivolts in here or 300 millivolts. The user of the IC doesn't care so long as the signal levels at the interfaces, that is the I/O of the chip, are within specified tolerances. And so at that point, the swing levels, the voltage levels, current levels need to be specified in absolute terms, that is, in terms of a specific number of volts or amps. So it's usually there that we need to make use of reference circuits. There are also circumstances where bias circuits rely on reference circuits to help them establish healthy operating points internal to the IC. So those are two of the main ways that we use reference circuits. So since we rely on a reference circuit to generate a voltage and or current of a known fixed absolute value, we have to think about components, devices, or anything really on an integrated circuit that we can use that can generate these absolute constant values. And really there's very little on an integrated circuit that doesn't vary with temperature or with process variations or with supply voltages. It's really not, actually, in fact, it's not easy to generate a specific a reference circuit, which is why at the start you always need to consider whether a reference circuit is truly required, or can you really just get by with a bias circuit. Now, if a reference circuit is absolutely required, for example, at an interface, then one of the few absolute constants on an integrated circuit is the band gap of the material itself, the band gap of silicon. That is something that doesn't change with temperature or process variations. As long as the circuit's made out of silicon, you've got one constant there that you can grab onto. And since that's one of really the only absolute constants that's a property of the chip itself, people have over the years developed many clever circuits to produce a voltage that is somehow deterministically related to that constant. Some of them produce a voltage that's actually equal to the band gap of silicon through clever combinations of transistors and other devices. Even though the transistor and resistor values may vary over PVT, somehow the voltage they produce depends only on the band gap of silicon itself. Sometimes it's actually equal to the band gap of silicon. Sometimes it's a sort of fixed ratio of the band gap of silicon. So such reference circuits are often called band gap reference circuits, and they will be our focus. So although, as we said, there's many different clever circuits developed to generate a band gap reference, most of them are based on the same principle. And it begins by looking at the forward voltage drop across a PN junction. Now you can realize that as a diode or a bipolar transistor. Even if you have a CMOS process, it turns out that you clearly have PN junctions everywhere. So you can, in any case, push a current through a forward biased PN junction and that thereby develop this forward voltage drop. We'll call it VBE, the base emitter drop, assuming that the PN structure is a bipolar transistor, but in any case, it can even be just a simple PN junction. Regardless, let's label that forward voltage drop VBE. And over here is a detailed expression for VBE. We won't take the time to derive it, but I want to point out that there's many parts of this expression that depend on temperature. Some parts are cause VBE to increase with temperature, and other parts of the expression decrease with increasing temperature. So the dependency is complex and it's hidden in many of these terms, but the key point is that at temperatures around our interest, so let's say room temperature, even room temperature plus or minus, 50 degrees, the dependence is there's a negative dependence there. So that is temperature goes up, VBE goes down. Uh, the value around room temperature is often in the range of -2 millivolts per degree at room temperature. Um, it could be a little bit less than that, and it'll deviate from that value as you change the temperature. But in any case, it's referred to as an inverse proportionality. So VBE is said to be inversely proportional to temperature. But keep in mind, when we talk about temperature, we're talking about the uppercase T here, which is in fact absolute temperature. So it's inverse, the VBE is inversely proportional to absolute temperature. And you may sometimes see the acronym IPTAT for short. So the first, again, making a very accurate bandgap reference is actually quite a complex task, quite a complex circuit. So first thing to ask yourself is, well, is that accurate enough? Right away, you've got a voltage drop here, VBE, that's only varies by about 2 millivolts per degree at room temperature. If your application can put up with that kind of variation, you may be done right away. There are other trivial ways like this to generate voltage references. For example, you can simply rely on the supply voltage itself and perhaps use a resistive or capacitive voltage divider between the supply voltage and ground to produce a reference voltage. Now, such references will vary with supply voltage variations, temperature variations, but in any case, you know, you have to think about how accurate your voltage reference needs to be. But let's say that that's not accurate enough. You require a temperature, you need a reference voltage that has a temperature coefficient less than a millivolt per degree, let's say much less than a millivolt per degree. The bandgap reference principle is to somehow make use of this IPTAT voltage VBE and to somehow superimpose on it or add to it a voltage that is proportional to absolute temperature. So you have the IPTAT voltage of VBE, and you somehow have to create a PTAT voltage, and then you have to scale it by a gain constant K so that the result over here has the exact opposite temperature coefficient as your IPTAT voltage source. So let's say in this case, the IPTAT voltage is -2 millivolts per degree at room temperature. Once you generate a PTAT voltage, you've got to scale it by the appropriate constant K so that this voltage here has a temperature coefficient of about +2 millivolts per degree Kelvin. And then adding those two, the temperature coefficients will cancel and you'll end up with a perfectly constant, a voltage that doesn't change across temperature variations. And of course, you have to take other measures to ensure that it also doesn't depend on supply voltages. Um, so you need to use, if there's any amplifiers or current sources involved, they should have good power supply rejection and so on. And then you can arrive at a stable voltage reference. Now, if many of the, especially early techniques for doing this would produce a voltage that was actually equal to the band gap of silicon, but more recent, you can see that this is actually not a small value, and modern technologies have supply voltages of a volt or less. So the old school techniques for generating bandgap reference voltages of about 1.26 volts are no longer implementable in advanced technology. So new bandgap reference circuits have been devised to make use of the same principle, but resulting in voltages that are below a volt. So the IPTAT circuit's pretty straightforward. Just make a current source and force a current through a diode connected BJT. What about the PTAT generator? Well, the way we generate a voltage that's proportional to absolute temperature is to, again, make use of the properties of forward bias diodes or BJTs. So imagine you've got two BJTs, one with an emitter area A1 and with a current I1 flowing in it, and a second that is a scaled copy of the first, and therefore with a different emitter area, A2. This can actually be made up of parallel copies of A1, so that A1 and A2 are related by uh, a quite specific integer multiple, and likewise biased by a current I2 that can be related to I1 with current mirror circuits, so that the ratio I1 and I2 are quite well established. So let's next define the current density of those two BJTs as being the current they're carrying over their area. So the idea is that you make two BJTs like this and you bias them with different current densities, J1 and J2. Now by doing so, it's straightforwardly shown that the difference between their base emitter voltages will be PTAT. So specifically, delta VBE, which we can define as VBE2 and minus VBE1, is just given by the natural logarithm of their ratio of their current densities, which again can be quite well controlled just by ratioing device sizes, and thermal voltage KT over Q. K and Q are obviously constants, absolute constants, so we're left with a bunch of constants times the absolute temperature, T. So this then is our PTAT quantity, this expression for delta VBE. So in summary, an integrated voltage reference is made by adding the forward bias voltage of an individual PN junction to the difference in the forward voltages of two PN junctions that are biased at different current densities. And just remember that before we superimpose or add these two voltages, we should scale them in such a way so that their respective positive and negative temperature coefficients cancel precisely. Now, especially the IPTAT voltage, VBE, does not have a perfectly linear relationship between temperature and voltage like this PTAT generator does. We saw on the last slide that the expression was quite complex. So as a result, the relationship between the IPTAT voltage and temperature is not linear. It's got some curvature on it. So in fact, we will only be able to cancel their temperature coefficients precisely at one temperature. Typically, this is done at room temperature or the nominal operating temperature of the circuit. And so, a detailed analysis will reveal that there will still be some mild temperature dependence as we deviate away from that nominal temperature. But that can be much less than a millivolt per degree Kelvin. And in fact, there's additional circuit techniques that people have developed to even minimize the curvature. These are called curvature compensation techniques for bandgap voltage references. So here's an example bandgap voltage reference circuit that can operate from a low supply voltage of 1 volt or even less. So to understand how this applies the bandgap voltage principle that we described in the last slide, let's start from the top. Recognize that the transistors Q1 and Q2 are biased with the same gate source voltage, and that the op-amp produces a feedback loop that so that the virtual short circuit between the op-amp's input terminals provides the same drain source voltage for Q1 and Q2. So they form a very well matched current mirror. And as a result, since they're ratioed M to 1, we know that I1 is equal to M times I2. Okay, the second thing we want to recognize here is that D1 is either a simple PN junction or perhaps a diode connected BJT. In either case, let's call this forward voltage drop across it VBE1, because it's certainly got some portion of I1 flowing through it in the forward direction. So this will be in the neighborhood of 0.7 volts, of course. And again, the op-amp ensures that very close to the same voltage appears here. So already you can recognize that there's some requirements in the op-amp here in order to ensure that the circuit operates properly. For example, it should have relatively low input referred offset voltage, and moreover an input referred offset voltage that's temperature independent to ensure that these two node voltages are matched. Okay, so having established those voltages, the next thing to realize is that the current, a portion of I1 that flows through here is going to be equal to VBE1 divided by the resistance there, which is RA over M. And the remaining current flows down through D1. So the current down through D1 is given by MI2 minus the current flowing through the resistor branch, MVBE1 over RA. We can then factor out M there. We end up with this expression. For the current through D1. Now moving over to the current branches on the right, first we've got a fraction of I2 that flows through resistor RA. And again, that's simply given by this expression here. It's got a voltage of VBE1 across it, and Ohm's law then tells us I2A. The remaining current flows through I2B. I2B is therefore the total current I2 minus that portion of current that flows through resistor RA. So it's I2 minus VBE1 over RA. So you'll notice this is precisely the same term here. So the current I2B is M times smaller than this current. Let's label this I1B, which means that there's M times more current flowing through D2 than D1 than through D2. Okay. The next thing to notice is that the area of D1 and D2 are ratioed. And this can be done with high accuracy in an integrated circuit simply by realizing D2 as sort of n integer copies of the diode D1. So now we've got the current density of diode D1 is the current flowing through it which is in fact M times I2B divided by its area. Let's call it A1. Whereas the current density through diode D2 is the current flowing through it, I2B, divided by its area, A2, which is actually N times A1. Because again, we're using D2 to refer to the N parallel combinations of copies of D1. So that tells us, putting these two expressions together tells us that J1 is M times N J2. So the diode D1 is biased at a current density Mn times higher than the current density of D2, where M and N are both ratios determined by the ratios of device sizes, specifically the ratio of Q1 and Q2 sizes and the ratio of D1 and D2 sizes, respectively. Okay, so the voltage VBE2 that arises here across diode D2 and the voltage VBE1, we know, differ by a delta VBE, which appears across the resistor RB. That delta VBE is our PTAT voltage, where the thermal voltage KT over Q is scaled by this natural logarithm of M times N. So M times N are variables that we can play with as designers to try to realize some desired temperature coefficient for this PTAT generator delta VBE. Now that delta VBE is kind of turned into the current I2B by the resistor RB. So I2B is itself a PTAT current, a current that is proportional to absolute temperature. If we want to write it out, right, we can go see that it's KT over Q RB times ln of Mn. Okay, now the one catch here is that the current I2B also depends on the resistor value RB. And remember that all resistors in an integrated circuit will have a value that varies with temperature. So the current is not precisely PTAT, but we'll take care of that later. So the total current then flowing down here, I2, is the sum of I2A which is basically a PTAT voltage divided by RB, and I2B, which is an IPTAT current divided by RA. So that total current I2 is mirrored over to I3 with a ratio 1 to K. So I3 is equal to K times I2 or K times I2A plus I2B. And that current gets pushed through another resistor R to produce the final reference voltage Vref. So Vref is K times R times I2A plus I2B. Now substituting in our expressions for I2A and I2B, you end up with this expression down here for VREF. The first term over here, that's our PTAT voltage, I to A times KR. And you'll notice the temperature coefficient of the resistor RA should be perfectly canceled by the temperature coefficient of the other resistor R. So the intention here is that both R and RA, and in fact the other resistors in the circuit as well, RB, RA over M, should all be realized in the same way, using the same style of resistor, for example, polyresistor, and should be matched with ratiometric techniques so that all resistors are either parallel and or series combinations of the same elementary unit polysilicon resistor. That way, their temperature coefficients should all be matched and should all cancel in the final expression for VREF. And at the same time, we can ensure that these ratios are fairly well controlled, right, as within the mismatch accuracy of the process technology. So this first term here in green has the PTAT, the IPTAT voltage VBE1, and a bunch of ratios. K is a current mirror ratio, R over RA is a ratio of resistor values. So sorry, that's the IPTAT quantity. The second term here is I2B times KR. This one is our PTAT source. You see the absolute temperature here showing up as a proportionality. Everything else in there are either ratiometric constants or absolute constants, K over Q. So as a designer, you have control over quite a few design parameters here. And most of them are, again, ratios of device sizes. You've got terms like M, K. You've also got the ratio of the PN junction areas, N. And you've also got the ratios of resistor values, R over RA and R over RB. So you select all these, as a designer, you select all these ratios in such a way so that the temperature coefficient of the IPTAT term precisely cancels the temperature coefficient of the PTAT term. Now, you see that you've got more than enough degrees of freedom to do that. You can use the extra degrees of freedom to control other desirable properties of the circuit. So you see, for example, there's no reason why VREF has to be above 1 volt. We can scale the currents I2B and I2A in such a way that they produce a voltage VREF that's, sort of whatever we want, really. We can make a relatively small bandgap reference voltage of a few hundred millivolts. Or we can make a larger one as long as we keep the transistor Q3 in active mode. And that's important because if transistors Q1, Q2, and Q3 are not in active mode, then they're not behaving as a very good current mirror, and we rely on their current matching for proper operation of the circuit. The other freedoms we have are to choose the kind of absolute current levels flowing on here. I mean, we can create the circuit so that the currents I1 and I2 are tens of microamps or hundreds of microamps, just depending on how we scale the values, all the resistor values together, and transistor sizes. So there we have a trade-off. More current will mean more power consumption, but may mean less noise. So proper matching techniques are obviously going to be very important to maintain these ratios. We need not just matching among the current mirror transistors Q1, 2, 3, also in the construction of the PN junctions D1 and D2 and the resistors themselves. And then even in the design of this amplifier that's performing the feedback, we require good matching to ensure low offset voltage, and there may be further requirements for good power supply rejection. Otherwise, um, changes in the power supply may affect the bias currents flowing, and alter the output reference voltage. Again, finally, this circuit can operate from a relatively low supply voltage of a volt or slightly less, but ultimately it will be limited by the fact that we need to maintain a VBE here. Oops. And that may be in the neighborhood of 0.7 volts. And on top of that, we need to have enough VBS voltage drop on Q1 and Q2 so that they remain in active mode. So it's difficult to operate the circuit far below zero point 0.9, or perhaps it can be pushed to 0.8 volts if you really push it, but that's sort of the lower limit of the supply voltage for this circuit. So when you're designing the circuit, you start out by getting a feel for the temperature coefficient of VBE1. This can be done with a simple simulation, and then selecting the ratios K, M, N, and the resistor ratios to give you reasonable values of current and keep transistors in active mode while still ensuring that the PTAT and IPTAT temperature coefficients cancel at your nominal operating temperature. And then you can perform simulations of the overall circuit, sweeping temperature to ensure that the output voltage Vref remains relatively constant across temperatures. You'd likely also want to check things like the supply voltage, the sensitivity to supply voltage variations, and of course, stability of the feedback loop formed by the op amp. Now, since bandgap circuits rely on the forward voltage drop across PN junctions, some question may be raised about their compatibility with CMOS technology. But of course, even in CMOS technology, we've got plenty of PN junctions floating around, and so people come up with clever ways to make use of them to implement bandgap circuits. Here are a couple of examples. The one on the left is perhaps more common, where you've got a P-type substrate into which an N-well is deposited. CMOS technologies will generally have the ability to do that because it's inside of these N-wells that PMOS transistors are realized. But rather than putting a PMOS transistor in this N-well, we're just going to deposit one P plus region. This is essentially like a drain or source region of a MOSFET, but then we don't have any gate for it. We just make use of it as a P-type region inside of an N-well, and then with the P-type substrate underneath, we've got a sort of PNP structure that we can use as a BJT. Now, since we're just going to ultimately diode connect this BJT, we're going to short together the base, N-type base, with the P-type emitter. We're really just using it as a diode in any case. So we really don't care about the BJT's performance in terms of its beta. It will have a very poor value of beta. It will also most likely have poor high frequency performance. But neither of these things matter much in bandgap circuit applications. So you can use, this is one example of a structure that can be made in most any CMOS technology. Some variant of this can be made and allow us to realize the junctions that we need for bandgap circuits. Now, most bandgap circuits, including the example we studied so far, result in a reference voltage that's a constant. But what if you require a reference current? Well, this is just a general technique for converting reference voltages into reference currents that's quite useful. Essentially, the idea is to take that reference voltage and apply it across a resistor, giving rise to a current that is equal to the reference voltage divided by the resistor value R. Now, this can be done using the simple feedback circuit shown here. Assuming the op-amp has high gain, there will be relatively low differential voltage here. So Vref is essentially copied across the resistor R, and the op-amp provides whatever gate voltage is required so that the PMOS transistor sources this current, Vref divided by R. Having generated that gate voltage, we can now reuse that same gate voltage to drive additional PMOS transistors to generate copies of this reference current. So this is a way that we can then distribute a reference across a chip. We can make as many copies of this reference current as we like, and we can scale them by whatever factor M we like just by ratioing the PMOS device sizes here. And then we can send those currents all the way across the chip where they can be converted back into a voltage by connecting them to another resistor. So the current that's distributed here, let's say to be consistent, let's call this Iref over M. So therefore the current Iref that's being distributed is equal to M times Vref over R. So if we then put that across a resistor whose value is R over M, which we can build that by essentially making M copies of the original resistor R in parallel, then we end up with the same reference voltage Vref here that we started with. So again, although let's consider the case where these resistors R and R over M are realized as polysilicon resistors on chip, they will have a temperature coefficient. So the reference currents Iref will not be constant, absolute constants. They will vary with the temperature coefficient of polysilicon resistors on the chip, but as long as the resistors are relatively well matched, we can recreate the bandgap reference voltage Vref wherever we need to, anywhere across the chip. And we cancel the polysilicon resistor temperature dependence because, again, we multiply Iref times R over M. So the M over R gets canceled here. Okay. Now, if you absolutely require an absolute value of current, like a specific number of microamps to be delivered, that's actually quite a challenge on a fully integrated analog circuit, because although we have the band gap of silicon, which is an absolute constant number of volts, there's no equivalent current constant that we can grab onto and make use of in a silicon IC. We can generate the voltage, but there's nothing with units of ohms that doesn't vary significantly across temperature that we can fabricate on an IC to convert that into a current. So really the only way, the only reliable way to get an absolute constant value of current is to use this same technique, but to make R an off-chip resistor. So if we have a pad here, okay, then we can make our precision resistor off chip, and the resulting current that flows down here will then be a band gap voltage Vref divided by precision resistance R, and then it will therefore have a very tight tolerance across temperature. And we can use that however we like on the integrated circuit. The cost of that is essentially that we need an extra pin on our chip to allow for the off-chip connection of the precision resistor R.